Good afternoon, everybody. Welcome at the third webinar for Healthy Building Design Competition from RIGWA. My name is Lada Hense-Centnerwa. I am one of RIGWA's vice president, and I may now moderate this webinar. Actually, the only thing is to introduce speakers. So let's go first to the first speaker, Marcel Schweiker, who is already here prepared from University in Aachen, Germany, and he's going to tell you something more. Well, he's expert in about healthy buildings. So please, Marcel, go on.
Thank you very much, Lada. Give me a second to share my screen and check that all is fine and you can see my screen.
I can see it. Yes, we
Very
can
good.
see it.
Yes. So good afternoon also from my side. My name, as Lada said, is Marcel Schweiker, and I'm from University Hospital in Aachen and also have a chair at the Aachen University. And I will talk a bit today about human building resilience and healthy buildings. And compared to the previous webinars, I think I will be more, let's say, on the conceptual level, and hope I can give you as the students who are going to compete in this competition a few thoughts to think about when looking at school buildings, how to design school buildings, and also how to design buildings in general, and what should be your target ideas and target concepts in that. So as we all know, we will face severe problems due to climate change. And we also know that this rising heat is affecting the health of many people, both outside but also inside the building. We will have a huge number of heat waves coming alongside, and therefore also severe conditions coming from outdoors into indoors. So we need to prepare our building stock to that so that humanity can be still productive and comfortable inside these buildings. And one possibility could be to say, okay, we cut down all what we have outdoors by active means, for example, active cooling, in order to, let's say, relieve ourselves indoors from these external severe conditions. But at the same time, I think we all know that buildings are already responsible for 40% of the energy use and 36% of CO2 emissions, and that we have to be conscious about the solutions we provide for the buildings, also to what extent they use energy. And luckily, besides, let's say, this tendency toward energy efficient building, which I would think started several decades ago to see how can we make buildings more energy efficient. There's also, let's say, a trend to more and more talk about healthy buildings, or as said here, healthy buildings for healthier buildings. And I would say, while it's probably rather straightforward to calculate the energy consumption of a building, of course, you have to do some assumptions as well for that phase. It's more tricky to, let's say, see what is really a healthy buildings and how do we design these healthy buildings. And that will be, I will give you a perspective on that from what I have learned. So to start with, I would like to start with some key terms and concepts related to health, because, well, the prominence of healthy buildings also comes to that everyone is talking about healthy buildings, but at the same time, I'm not really sure if everyone is talking about the same thing and what people really mean with healthy buildings. So a few concepts from my side. First, health for me is a multidimensional target, which includes physical health, psychological health, and social health, and all of them are influenced by the buildings we build. Then I tend towards the health-disease continuum, which considers health not as a binary model like the biomedical model, either you're healthy or you're ill, but there's a continuum between you being healthy and you having some disease. And we have to distinguish between self-evaluated, let's say perceived health, and externally assessed health, for example, by a medical doctor. If we put these together, it's a figure here, still in German, but I think with the words above, you can figure out what it means. A concept from health and medical sociology, where you see that we have the three dimensions. We have the continuum from the status of health to disease, and we always have for each of them the perceived self-evaluated health and the externally assessed one. And I could feel very healthy, but at the same time, maybe I haven't been to the doctor for many years, so maybe there is some disease I carry with me. So if I would go, the externally assessed health would be different. Then it's important to think about health as to promote health in two ways. One is the pathogenetic view, that we want to see and how diseases develop, and also want to avoid that diseases develop. On the other hand, we have the phylogenetic view, which looks at how we can promote health, how health can be developed and people can be strengthened. And therefore, also for me, if I talk about healthy buildings, for me, this is always short for health promoting buildings, because the building itself might not be healthy, but the building should be promoting health for those inside the building. With these key concepts of health, we can define requirements for healthy buildings, but we also need to look who is using the building. And the photo, the image, the AI-generated image I'm showing here is showing you that there's not a single average user in the building, which you can clearly define what needs this user has. In contrast, there's a multitude of users with different capacities, with different preferences, with different abilities, and therefore also buildings need to be rather flexible for this diversity of users. And we may need to find out, okay, how can we serve in, let's say, in a perfect case, all of them, but preferably like really most of them. And that gives some challenges as well because of these differences we see. If we look at the literature to healthy built environments, you can find a multitude of concepts. I just put a few in here on the slides. One here in the middle is the one by Esther Sternberg from USA, from Arizona, which I like, put the air quality as one parameter at the foundation of a healthy building, and then several elements like light, views, biophilia, acoustics, spatial layout, and environmental control on the sites, which all of them combined lead to health and well-being in workplaces, which is her topic. On the right side here, you see the 9 foundations of healthy buildings by Joe Allen, which has similar but also some distinct factors. And you also see here in the bottom left, you see a latest publication, the Healthy Buildings Barometer, which was published in Europe to also try to categorize a bit what can be conditions for healthy buildings, either residential or office buildings. So we see there's a multitude of factors. But for each of the factor, we need to see, okay, how do we deal with this? How do we set requirements for this and standards for that? And with that, I will come to the discussion of what approach should we take to set certain standards or certain requirements for these parameters. And I will do this now from the perspective of the human being and introduce one concept which is deriving from psychological health risk assessments, which looks at the difference between stress and strain, which is maybe in English not that easy to distinguish, but in German we have, that's why I put some German words here, we have very different words for some parts. But if we go through this model, we see that on top here, you have workload, the physical conditions, the social and organizational conditions, and societal factors, which all combined are a stressor, some demands, and in German Belastung, which come from outside to the individual human being. And in this concept, all these factors you can quantify. You can quantify the workload, the physical conditions, and so on. But then we enter the individual, and based on the inner characteristics, the preferences, physiological constitution, and other factors of the individual, these stressors lead to a certain strain. And I don't have it with me, but usually I show a picture that if you have the same weight, for example, to carry a heavy weight, a completely untrained person would have a really high strain, while, let's say, a bodybuilder going to the fitness studio would have a low strain to carry this weight, while this weight, which represents the stressor, is the same. So the same objective stressor can lead to different strain in people depending on their characteristics. And if they have this strain, this could lead to adverse effects, meaning short or long-term weakening of the person or a disease of the person. So the first approach, we should look at how to relieve people from these stressors, how to minimize harmful exposures. But the question is that the only concern we have, or do we need to have more approaches when we talk about healthy buildings and not just about conducting assessments to fulfill all standards? So let us look at the case of relief. Relief is nice, I have to confess. Maybe some of you watching me now, they would like to be in the situation on a beach close by, really unstressful conditions, very relaxed. The problem is, over the long term, this is also potentially not the most healthiest way to live. One example where it's very easy to measure the effect of long-term relief, or let's say doing nothing, comes from muscle training. So here, a paper from 2016, which shows the decrease in lean body mass and also in the size of the quadriceps after 1 week of bed resting. And we may also consider that also our thermoregulation or other systems which deal with environmental stressors, they sort of decrease over time when we solely focus on the relief from these stressors. So there might be more we have to deal with than only the relief. And one concept which might help us to see what is the target at the end is what I call human building resilience. And there's a chapter where you can go more into detail about the backgrounds of it, with which I would like to explain what I think could be better approaches towards healthy buildings. If we quickly go through what resilience means, also here you see I'm a friend of trying to define things. I talk about resilience coming from the Latin words bouncing or bouncing back. And I put it in red here, except for some period 400 after Christie, where it had a negative connotation, a person unhappily backing away or distancing themselves from what is going on. Since, let's say, 1858, in different disciplines, it has a very positive connotation. And we can see different relationships described here. The ability to absorb change and disturbance, maintain the same relationships, capacity to recover, toughness, elasticity, ability to cope. Or if we look in building science also, we could talk about robustness of the human building system. And for me, it's important that we look not only at the building, but at the human building system when we talk about resilience. This is a figure from the chapter, which you see here, the reference below, which tries to, let's say, represent this resilience framework. So we start here in the A part, the challenge. This could be a heat wave, starting at some point, remaining some while, and then going back, pointing. And depending on the characteristics of the building, we see, let's say, a similar reaction of the indoor conditions, the stressors to the people. So it could be higher indoor conditions, so a higher stress for people, a bit maybe a timely offset, depending on the thermal mass of the building and other characteristics. And then at some point, we have also here the relief. At the same time, when we talk about human resilience, we could see that maybe also the strain for the individual individual human might rise due to this stressor from the indoor environment, stay a while, and then go away. And this endpoint here could be either because the external stressor finished, could be because the human being did some interaction with the building, maybe switched on the AC, went out of the building into a park, or maybe some automation system stopped the stressor. This doesn't matter. If we look then at, let's say, what is shown here to the left repeatedly, if we only focus on relief, we would kind of try to have the building resilience, so this middle part here, as high as possible. And therefore trying to cap all the loads we have from the environmental conditions to a minimum, so that we have a theoretical maximum value of relief between what would be if the building is poorly designed and the building we do. And also we see here, we would have a high grade of relief for the person, because compared to what would happen in this case, the actual strain for the person is quite minimal. But if you now look back at the example I showed you for the muscles, if we always have relief, we might have a problem in the long term that the building in the optimal case remains robust, resilient, or how you call it, but the human, due to not having enough training, might get weaker itself. And so the whole human building system gets weaker. So I believe that something is missing if we only focus on relief. And some may have guessed it, there's also, let's say, a blank spot here in this figure. And a strain does not necessarily always have to lead to a reverse effect. It can also have a stimulating effect, which leads to short or long-term strengthening of a person. So I think besides relief, we also need to design buildings or conditions for people to spend their life in, which have stimulating exposures and which encourage something. Some background to that. So far, often the focus is on avoidance of distress and workplaces, which often leads to stable conditions. But we also have eustress. This means a positive stressor, which then leads to encouragement. And in the best case, even as later studies shows, dynamic conditions that not only lead to eustress, but to pleasure or something called allisthesia. And there are also some advantages for some energy efficient measures with that. Even put more into the extreme, there are studies mainly also from, let's say, the neighbors to Aachen, from Maastricht, which show that even conditions which are outside the comfortable ranges, so exposures to cold conditions, or also a paper by Palubinski and colleagues, warm exposures, outside the comfort range. Let's say in these cold conditions, we talk about 15, 16 degrees C people we are in. In these warm exposures, we talk about 35 degrees C people are spending several hours in. And these studies show that these conditions outside, let's say, classical comfort ranges we see, they have positive health effects. For example, increased insulin sensitivity in patients with type 2 diabetes, and increased insulin sensitivity is good for people with type 2 diabetes, or a decreased fasting plasma glucose and insulin, and decreased mean arterial blood pressure, which is also a positive health effect. And well, if we summarize that, and if we see what could also happen if we have, let's say, conditions which vary a bit more and give people encouragement, we also may be producing intentionally or unintentionally some notion of pleasure. And I'm having a background in architecture, and I really like this image of trying to have people to really benefit, to really enjoy being in buildings. Of course, there's the question, how much pleasure do we need? That's an open question, I think, that still needs to be answered by more research and also practice. For those interested in this topic, I really recommend the book by Mark Decay and Gail Brager, published last year, Experiential Design Schemas, which gives a really excellent scientific background, but also a lot of examples how to create pleasurable conditions. So coming back to the human resilience framework, if we do not solely focus on relief, how could this look like? We go here to the far right, where we see, okay, we did not make the building as resilient as we could do, potentially even saving energy by doing so. So we do not cap this environmental stressor completely, but we leave a bit of encouraging stress for the human being. Then the strain, of course, might be a bit higher than compared to solely focusing on relief. But we have encouragement, and in the moments here, for example, when people are relieved from this encouragement, even some enjoyment. And well, it's a hypothesis. It's something we really need to test and research more on. But the hypothesis would be that with such conditions, the resilience of the human being, the same like going for sports, for training, would increase, the human being would be strengthened, and thereby the whole building system. So the three components or the three approaches I would like to see, if you manage that, would be to, of course, look at relief to minimize the harmful exposures, but also think about how can you encourage people inside the building, and how can you create pleasure and enjoyment. There are a few challenges I don't want to omit here. One is multisensory conflicts. For example, if you look at glazing, there was a, let's say, trend towards very high glazed buildings, due some of them claiming, okay, we want to have really high daylight availability for the people inside. So we want to really focus on, let's say, the visual domain. At the same time, especially now with increasing heat waves, we also have to consider the high thermal gains. And well, for some reasons, let's say external shading is still not very popular in some groups of designers. So we still need to put some sun protection glazing to reduce the thermal gains. And this is sometimes done with some reflective sun protection glazing. The problem is with these that especially in this area, I couldn't go into details for today for the short presentation, but areas which are very important for circadian rhythm, which support the suppression of melatonin, which is important during daytime. Especially these areas, you see that the sun protection glazing really reduces the transmittance. So besides adding glazing, you might reduce the important blue wavelength transmissions relevant for melanin suppression during daytime permanently, because you cannot switch that, and thereby have a conflict between thermal and visual conditions. Another conflict we always have to think about is interpersonal conflicts. Of course, we can put active means to our flat. We could do whatever we want in our flat, but there might be a downside for a neighbor. I always wonder, if I look at this window, if I would like to sleep there with an open window during nighttime, whether it would be possible for me or not, given that all these machines from my neighbors emit heat and also noise when running. There's also a challenge of extremes. A worthwhile study to read, which was highlighted in this New York Times articles from 2021. What happens if we have a combination of blackout and extreme heat? The authors of this study called it maybe the deadliest climate-related event we can imagine, because if we design buildings, let's say, for some sort of thought resilience, which is relying on electricity, in these conditions, which at least in some countries happen more and more often due to the increased use of electricity for cooling, and a non-stable system might lead to really severe conditions indoors. There's also a point of time. the same stressor, or maybe even a pleasant stressor like a fruit salad, which probably, at least I usually ask my audience, and let's say 95% of them, they like fruit salad, and most of them believe it's healthy. But let's say the perception of this stimuli, which first is thought of positively, changes when I tell people, what if you have to eat fruit salad, only fruit salad for 1 week, for 1 month, or even your whole life? Coming to the individual, I really like to, let's say, promote the use of personal environmental comfort systems. There's a lot of research going on, which shows that it is able to reduce energy consumption while providing really a high level of control for the individual people, and also high satisfaction for individual people. The question is still open as to what extent do people then take the challenge, take the encouragement they need. If they can do all, provide them with comfort by the PACS systems. So to conclude all of these, what do I think would be consequences for design and operation for building? And I would be happy if I see some of these considerations also in your healthy buildings contributions. First, I would like you to promote, to consider resilience holistically, with an emphasis on trying to increase human resilience in the long term and not solely trying to make a robust, very resilient building, which means design and operate with opportunities for adaptation and anesthesia, sketched here to the right. Top, like not only consider tight temperature control for relief, but also try to see where can you include some elements of extended range for encouragement. The second is design buildings, of course, at the same time that give people time and opportunity to adapt, because we know that, for example, the physiological adaptive processes, they take 4 or 5 days. And if the heat wave outdoors comes from one day to the other, we need to have buildings which can sort of slowly let people adapt to these conditions. Consider resilience beyond the individual building. That was the example of all the air conditionings of my neighbors. And I think a point which also by Berster is often mentioned is provide sufficient individual, but also understandable and efficient adaptive controls, so that we can really look at the individual buildings, individual humans and their needs. And a last point, which is, let's say, summarized very well in the new European Bauhaus toolbox, consider these 3 major points: sustainability, inclusion, and also beauty. With that, thank you very much for your attention. And I'm not sure if we have questions. I will give the word back to you, Lada.
Thank you. Thank you, Marcel, very much for your conceptual principles for buildings with the newest, latest research and ideas. Yeah, it was in a general conceptual. I just maybe want to just make sure that students, yeah, of course, they have to design a school. And so then, yeah, I also like very much that idea of that it's healthy to go outside of thermal comfort zone. That research from Maastricht University, but yeah, they just shouldn't think that yeah, then design a school for outside of thermal comfort zones is the best. It's yeah, about the fluctuation, and of course in school children, they go outside to play outside and they get different environments. But thank you very much, and I think we should have questions at the end, or yeah, or is there any question right now for Professor Marcel Schweiker, who is also member of the committee or jury? So he's going to evaluate, and he has much experience with his own students. nobody dare to put up a digital hand and to ask questions? Okay, then maybe if there would be a question, then please put it in a chat, and then we come to it later. Yes, Marcel, you will stay with us until the end.
I will try as long as possible.
If
Yeah.
if you may. Okay. So once more, thank you. And now we go to our second speaker today, Pedro Vicente from Spain, who is also one of RIHUA's vice presidents, and actually on behalf of RIHUA, he is organizing this competition, and so he is expert on energy. So Pedro is going to tell you some notes about and advice for design in terms of energy. Yes, Pedro, floor is yours.
Okay, thank you very much. I'm going to share my screen. Okay. Can you see my slide? It's okay?
Yes, we do.
Okay, so I'm going to start. Okay, yes, I'm going to talk about facilities and energy efficiency. I mean, my presentation maybe will be more practical. I'm an engineer. I'm a full professor at the university. I'm teaching about facilities, most of facilities and energy efficiency. And I tell you that the objective is that the solution that you have to give to this problem should be achievable, feasible. It's something that someone can do. Even if what Atzke say, the president of the jury, they are going to appreciate more the conceptually solutions in a conceptual mode, but the question is that should be something I mean conceptual, but it's something that someone can achieve. It's something that can be done. So this is the photograph. I tell you that my presentation will be more practical, more or less, to see the problems of this, to make this renovation, to make this renovation that they want to have. And I tell you that this solution should be something achievable. Well, this is the data that Livio Mazzarella gave us in the first presentation. So we have 21 classes. I think here I can write, yes. We have 21 classes, around 26 students for every classroom. This is in Milan, and we have these degree days, and we have also this heating section. So this is the not only the buildings, you know, the around of the building, which is more or less small. It's very small, because maybe in some of your solution you have to, or maybe you can propose to use external parts of the building to put some facilities. Maybe you can. I mean, you can use the ground, you can use the roof, and you can use all as well the external part. But the question is that, I mean, it's not only the building, but the surrounding of the building is not very big. It's more or less small. So now they have two. I mean, they have 3 boilers, but one of them is working as backup. So they have this power for one boiler, and this one for the other boiler. So it's around 450 kilowatt of heating power, which is a lot. The system works with radiators, water pipes, radiators. They have also electrical boiler in each toilet. So this is a very few efficient system that they have, but it's the used system in many schools, not only in Italy, but also in Spain. So it's something typical to have this solution without cooling and without ventilation. So they have only radiators and electric boiler in its toilet. So it's a system very few efficient. So the facilities are very old. So this is located in a space under the ground. So here you have the 3 boilers. I tell you that one of them is working on backup, very old ones. They have also very old tubes, and they have some problem in asbestos problems. So they have also to remove all the insulation because it's made with asbestos. This is the floor, the ground floor plan. You have to think that this space is in the underground. Here is when we have the boilers. The boiler are more or less here. This is the boiler rooms. So look here, the chimney here, and it's also here. This is because this goes down this part. The same of these spaces which are underground. This part is represented in the drawings like this, but you have to think that they are in underground of this place. We have also a first floor around 1,100 meters, square meters, and second floor around also around 1,100 meters every floor. You have around 10 classes in first floor, another 10 classes in second floor, 1 class in the floor, in the ground floor. Moreover, the classes you have also laboratory or painting rooms. So the students, you have to think that maybe the students are here and they can move to this class, to the other class. So simultaneously, you have these 500 students, but I mean, in these 21 classes, but the other classes and other spaces will be used, I mean, depending on the class. So I just to say that not all classes, not all spaces are empty, are full at the same time, no? But we have to think that we have these 800 students, I mean, 21 classes with 26 students in every class, and maybe in some time they move to another class which probably are less used. Well, these are the challenges that I would like to talk. I mean, for me, doing the renovation, the main challenges are these two ones. First, we have to improve the indoor air quality because now they don't have any ventilation. And the other question is that I think that all the solutions that you are going to propose should be decarbonization. You have to, I mean, make proposals of, I mean, situations with, facilities that don't have CO2 emissions. So probably you have to have these carbonization solutions. So if we talk first, the first challenge is how to improve the indoor quality. So here you can see the glass. What I tell you, here you see the radiator, one radiator, other second radiator is here. You have these windows. Here the door is open. So this is very nice because, okay, you can open the door and then you have very nice to have also outside. Well, the problem is that, for example, now in Milan, this is today, this is this week. So today we have the temperatures between 0 and 8 degrees. Tomorrow we have -1, 6 degrees. So probably when you have this cold weather, probably the doors will be closed, the windows will be closed, and then the air in the classroom will be very bad if you don't have any ventilation. If you see here, for example, here I put the weather in Milan. Probably there are more places to see. I mean, more or less the weather here. But for example, I found this. For example, in January, this year in January, you have like this temperature, you have lower temperature. I like to see the maximum and the minimum. You have -3, some days -3, 14. I mean, this is more or less the temperature that you had in January. But if we always also would like to see in summer, for example, in June, you have also temperatures, as seen here, for example, this year, the 28th of June, you have 33 degrees of maximum temperature. So this is the problem of the schools that they have in Italy, we have in Spain, or they are in many cities, which is the overheating. So we think that if you want to have a resilient building, probably you will need heating, but you will also would like to have cooling to have better condition in summer, and you need ventilation. Okay, one challenging for doing this is that the building has a very few height between the floors. I mean, this is something critical, and it's something that make it very challenging here. That here you see this, and you see here the size. So here from this point to this point, you have only 3.4 meters, which is very few. In Livio presentation, you could see that the distance between the floor and the ceiling, and you have the ceiling, was 3.2 meters, which is not much. So all the solutions should, I mean, you have to adapt this so this height of the roof, which I tell you that is not much, so makes it difficult how to propose different solutions. So for example, if we have these classes, we can see more or less how I tell you that even if you want to, and the jury is going to see the solution in a conceptual mode, in a conceptual sense, what I would like to do here is more or less to know what is the space, what is the room that you need to make this ventilation. So this is more or less the objective. So if we would like to have with this European norm that you have here, this 16798, here is in Spanish, but it's a European norm. You would like to have second category of, air quality. You need to put 7 liters per second, and you want this category, and you consider that the building, you can see it, that is very few polluted, or not few polluted. We see in the middle, for example, not few polluted, that maybe we can take. You have to put this ventilation per square meter. So we have this equation. We are going to use this equation. And for example, what the numbers I want to make here is that the flow rate that you need to have this ventilation, this minimum ventilation according to this European norm 16798. For example, in a classroom that you have around 27 person, 26 students plus the professor, and every classroom that is around 46 square meters, nearly 50 square meters. So you have 27 persons, and you have to ventilate 7 liters per person, plus you have a surface of 26 square meters, and you have to ventilate 0.7 liters per square meter. So the ventilation that you should have it to have this two quality will be something like this. So this is 32.2. Sorry, I'm going to erase this. 32.2 here. 32.2, which means around 221.2 liters second every classroom you have. So here you have some ventilation per person, some ventilation per square meter. This data, this is around 15% of the total ventilation, which means that even if you don't have anyone in the classroom, you should ventilate at least this 15%, just to have more or less an idea. So this is the calculation I have just done for a classroom in liters per second, according to this European rule. If you change from meter square per hour, you have this data. We can also calculate this to have the renovation hours. So the volume of one class, how many times you have all the air out, all the air inside. So it's easy. A classroom, we have 3.2 meters high. We have this surface, so we have this volume. So this flow rate that we divide by the volume. So we have 5.5 renovation hours, which is a lot. It's very high. It's not only from the comfort point of view, but also from the healthy point of view. 5.5 renovation of the whole air of the room every hour it's a very healthy situation in a classroom that we have now. So it's very high ventilation. Well, so this is one classroom, and this is the flow rate that we should have in one classroom. I tell you, I put category 2. You can put also category 1. Meaning the small children, maybe less than 5 years old, they used to consider category 1. But even in category 2, I mean, the ventilation is very high. If you have, instead of one classroom, you have 5 classrooms, then you have to multiply. So you have this. At the end, you have 21 classrooms, so you can have an idea what can be the ventilation, nearly 10,000 square meters per hour. Okay, this is just to know the numbers. I tell you that we are doing numbers, we are make some calculation, but I tell you that maybe the objective is conceptually, but even if it's conceptually, just to have this idea. So this is a chart to calculate the ducts that you have to flow the air into the space. So typically in engineer, every duct should be calculated around 0.71 Pascal per second of losses. Just to have an idea. So, for example, if we have one class, the pipe that you need to put to flow the air to a classroom should be a pipe around, you have here the diameter around 300, 280 millimeters of diameter. You have 5 classes, so you need about 500. You have the whole floor, the whole floor. So first floor, second floor, you want to put the flow rate of 10 classes for all the people in the floor. You need a diameter around 630 millimeters. That's just to go to this figure that you can, change from circular pipes to rectangular pipes, and just to have an idea. For example, for one class, maybe you need a duct of 300 millimeters by 225. For the pipe that you need for 8 classes, maybe should be around 750 millimeters by 300 millimeters. And the pipe you would like to have, the duct for all one floor, which are around 10 classes, you need 900 millimeters by, here you have, by 400 millimeters. So just to show that the size that you need is very important. And when you consider to make ventilation, you have to take into account this size at least. How are you going to put these ducts? How are you going to put this system? Moreover, if you see, for example, the ventilation, of course, you can do a ventilation like this. You can put a filter and then just put this here. Yeah, but the problem is that if you have here today 0 degrees and you want to heat this to 20 or to 21 degrees, for example, I put here, no 0, I put here -2 external, and you want to have here 20 degrees. For one classroom, just for one classroom, you will need around 5 kilowatts of power. So you have 21 classrooms, you will need about 121 kilowatt of power just to heat. For example, in this machine, you can do it. So you can have here -2, put this flow. For example, you have one classroom, and then you will need here 5.1 kilowatt if this is for one classroom. If you have this machine for the 21 classroom, then you will need more power, which is a lot of power. What is typical, for example, in Spain, you have to do by rule, is to put heat recovery. Is that use the heat that you have here in the room, take this air here, you have here -2, and then you can heat this air with this, heat recovery system. And then maybe with this system, you can hear -2, and maybe you have here 16, imagine, something like this. you can do for free because you use the heated air inside to hot the air outside. Okay? So with this, you can, for example, change the power and then you can decrease the power. For example, instead of needed 5 kilowatt, then you can need only 1.5 kilowatt because the efficiency of the recovery used to be around 75%. Maybe you can use 80%, but by rule, now with the European standard, it should be higher than 73. So probably you can select these systems of 75, 80% of efficiency, which are now available in the market. Why I say, I mean, there are two systems. You can have this plate system of recovery that you have here. This is a photograph, or maybe round system. This is something which is a wheel. It's a wheel which is rotating, and then you have this recovery. So why I say this? Because if you would like to see how these systems go, for example, here you can see here in the catalog. For example, just to show you, you see here technical data. For example, the machine that you need for a flow rate of 4,000, which is a classroom for 4 classrooms, for example, 5 classrooms. No? We say that 4 classrooms can be this maximum. Maybe you can rotate or you can select one of these. Just to show you that it's a machine that needs 1.2 meters by 1.5 meters. The length is around 3 meters. The weight is around 800 kilograms. So in this case, again, you should use around 4 or 5 machines for the whole building. So you have to look for the room. Maybe you can also use only one machine for the whole building, maybe something like this. With this ventilation, probably you will have a machine to hold the whole building. So, okay, look the size, look the weight that you have, and then you have to make the ducts to handle the air, to give the air to the 21, to the all classes of the building. So, I mean, just even I tell you, if you want to make the example conceptually, it's something that needs a lot of space, needs a lot of room, and you, in your proposal, you have to think more or less how are you going to solve this problem. If we talk about the system, maybe you can have this system of the air handling. This is the air handling unit. And maybe you can have this system for the heating or cooling here for one side, and here you can see here. In schools, I tell you that you move a lot of air, and sometimes you can do everything with only the air handling unit, which is this one, because you move so much air that maybe you don't need to have this system. You can do it only with this battery, just, heating the air to 22 to 24 degrees. It's okay, and then you can have this heating. In heating, in cooling, you have it at lower temperature. A system with this, you probably are going to have dams. You should have a CO2 measurement to control the air that is coming to every classroom to do an efficient system. Just to show an example, these are some photographs of a building that we have in the university. Some was renovated this summer, and here you can see the size of the system, the size of the ducts, which is not very nice. For example, in this case, just this was only done for improved ventilation. These classrooms didn't have any ventilation. So this was done to put the ventilation according to 1672. So look the size of the system, look the size of the ducts needed. Anyway, it's different because here at the university, we used to have classes of 100 people. So in the school, you have less people, so you don't need so much. But you need to have this space. How are you going to take out the air? How are you going to put down the air, and how are you going to put this ventilation? For example, this is a school in a historical building. I saw this last week, just to see the solution, for example, that maybe you can use the wall here, this side. This was historical. In Italy, it's very popular to do renovation historical buildings, which is very hard to, they are very hard to do. And for example, they are using the walls to put this heating or ventilation, for example, in this part of the building. This is a school building in Spain. So this is the first challenge, the improve indoor air quality. You have to select the equipment. What are you going to put in the equipment? How much? What's the flow rate that you would like to use? The ducts. How can you manage this? Which is, I tell you, very difficult, and it's a challenging problem when you make this kind of renovation that you would like to improve indoor air quality. The other problem, the second problem, is the decarbonization. How are you going to put the machine? Here, there are only some numbers. I tell you that, we have considered that we have ventilations with, these 800 units with very recovery, efficiency, heat recovery. So we need around 31 kilowatt for heating the air. And we have considered this surface in the building and a heat losses. This is just an estimation, about 50 watt per square meter. So we have considered that if you have a good building where it's good insulated, probably with 200 kilowatts you will have enough to heat and cool the building. Now they have 450. So now we think that maybe with only 200 kilowatt, maybe it will be enough. I tell you, just to have an idea about if we consider that we need this power, how can we manage it? What's the problem? No? I don't mind if it's 200, 250, 150. The problem will be similar. For example, I have been seeing some catalog, for example, in Clivet, just Clivet because it is an Italian company. So I think that it has been bought by a Chinese company, but it's Italian. Clivet is Italian. No? For example, here you see the catalog. For example, you can you can see the refrigerant. Maybe this is not the better one, of course not. Maybe you can change to another one, to R32, or maybe your proposal, you can put propane, R290, which is a natural refrigerant, but it's propane. So it's propane, so it's explosive. So most difficult to find a safe space to put these machines. So the question, for example, if you put this kind of machine, just to see that, for example, you will need here, no? Probably you are going to need around 200 kilowatts. So for example, the cooling, so probably you will need a machine like this or like this, probably, more or less, no? This one of these two model, just to see, even you have this heating capacity, you have to know that this is a 7 degrees external temperature, and in Milan maybe you have -2 degrees. So in these conditions, probably the power of the system can be around 70% the nominal power. So even if you see here 125, probably if you have a temperature of -2, the machine will not give more than 90 kilowatts. So maybe it's better to have one machine like this, because otherwise you will not have the needed power at this temperature. This is something that can be studied in the technical data. But I tell you that you have to think that at temperature lower than 7 degrees, the power is much lower. Well, the question is also the size. The size, the weight. You can see, if you see this size, one of these machines needs this length, this height. And you have to look.
Pedro, we are running out of the time.
Sorry. Okay, don't worry. Finish it. Okay. Yeah. So just to you have to look for this size. For example, then here I put some pictures. I mean, maybe you can put here in the underground, but then you have to think more things to what you can do. Yeah? Well, the other question is the gym. Just to for example, here in the proposal, you can put like this, or maybe you can put a dedicated system for the gym. Just as a proposal, I consider that the gym has a very different timetable, so you can put a system only for the gym, for example, or not, or you can do it like this. And the last question is the domestic hot water that you see we have electrical heater, and maybe you can put heat pumps, maybe a small heat pumps in every toilet, or maybe a system with heat pumps for the whole building. Just a question to solve, but I think that you should have the domestic hot water with this system with heat pumps. And finish. Just to, I tell you, maybe I have been too practical, but the question is that even if you want to solve it conceptually, I mean, the solution that you, I would like that you give should be something that somewhat can be achieved. It can be achievable. Should be solution feasible, and you have to try to solve all these challenging questions, which are very difficult when you have a renovation of a building like this. And thank you very much.
Well, thank you. Thank you
Well,
for actually very detailed, practical, but I think very useful example for design. And yes, and now we already have a quick question. So you can, it's heating, Pedro, is for you. Quick question concerning heating of the gymnasium. Which boiler is connected? But again, told that the secretariat is fed by the second heating. Well, I don't know if you want to answer this question. I just
I
wanted
don't know.
to.
I haven't seen. Okay, I see the chat. I haven't.
Yeah, in
Okay,
the
now
chat.
I see the chat. The heating
Then
was.
please. Yeah.
I mean, I think maybe the gymnasium at present they don't have heating. I mean, I don't know. For example, here in Spain, it's typical that we don't have heating in gymnasium. Probably we have cooling or nothing. So the question is that probably they also don't have ventilation. So probably in the gymnasium you should put something for the ventilation and maybe for cooling. I mean, just. For example, in Spain, we have ventilation and cooling, never heating.
Sorry,
I
Pedro,
think
can
that
you
at
stop
present they
sharing?
don't have. Yeah.
Can you stop sharing?
Yes, of course, of course. Yes.
I just wanted to say that it was like a very good, practical, detailed example, but just that example of these ventilation units, I think it was just in a terms to see how big actually it is, but that in that conceptual design, students, they don't have to go too detailed to actually to design, to choose a real ventilation unit. It was example to see how big it is, right?
Exactly. But the
Yes.
question is that they get, what I would like to say is that okay, they cannot say okay, this is with 1 square meter I can put it. No. I mean, you need the size at least to conceptually. I mean, make something that can be done, something reliable, because otherwise the problem is that you can. I mean, think that you can put the machine in very small, and then at the end is something that cannot be done. So what I think is
Yes.
important is that should be something that can be done. So
Yes.
of course, it's much better if you can make. I mean, to model the building and to make modelization, to do energy consumption and everything. But I mean, I think at ASCE, he said that they want the jury is interested in having a more conceptual solution.
Yes.
And I just would like to make some these numbers just I mean, that they try to see the problem, how difficult is the problem to look for this site. You can put 1 machine, 2 machines, 8 machines. You can do it in many ways, and every way is difficult to solve this renovation.
Yes.
It's difficult.
Yes.
Yeah.
Yes, renovations are difficult.
Yeah.
I am now here sharing general competition criteria, just to remind to everybody that how it's going to work, that actually there are like 5 main challenges where you get points for. And so then this is that overview, so that all of them needs to be addressed. Now there's now there's again question about secretariat. Yeah, I don't get it. Maybe then you can send this question about secretariat, which is it a room in that school. Maybe Marie, can you actually take this question and send it to Livio, who actually is from Italy, and he presented details about the school?
Yes, of course.
And so then how will it work? How can you then you will let know to that person who asked, or how can we solve this?
Anyway, I think it is in the ground floor. That is in the direction room. I think so. It's
okay, but then
I think so.
If I have this person email address, or maybe you can put it in the chat just to make sure.
Or you can also later in Teams write a message here in this meeting, isn't it? Or now, okay.
Okay.
Now you got email.
I have this email address.
Okay. Are there more questions? Or is there, Marcel, anything you would like to add?
I think the question on the gym and Pedro's answer, I think, is very nice also to question a bit what is the sufficiency? What do we really need? Do you really need a heating device in an Italian school gym when students are very active? Or how many hours a year would you need that, and what would be really like a sufficient and a good solution for that? I think relates quite well back to my talk that we really need to think what can we afford, also environmental, and what is good for the health of the children. And I would say that also what you mentioned, Lada, of course, we shouldn't design a building which goes up to 40 degrees C, but especially also especially children, they are considered as vulnerable, but they also need to have some encouragement to be trained. So I think that's, let's say, finding the balance is a tricky part.
Exactly. Pedro, do you want to add something?
No, that is, I mean, I think that now the schools in Italy, in Spain, in many countries, they are going to put more cooling, because it's also a question of healthy, because maybe in a gym like this, you can have 30, 35, 40 degrees in summer if you don't have cooling. So finally you have to stop and don't use the gym anymore, because otherwise it's bad for the health. So at present we have most of them with cooling, but not heating. The heating is not a problem if you are doing gym. Why not?
I also now again I am sharing. I found a question. I just wanted to highlight question regarding that Pedro, you used standard for ventilation. In frequent asked questions, was put that do designers have to comply with any specific regulation or building codes for this competition? And actually the answer is no. These standards, which are known and European standards or SRA standard, are actually more as a guiding. So you don't have to actually apply exactly the now valid standard if it's in Italy or your country. It's actually like guidance. Yes. So if there are no more any questions, I would like to thank both speakers today. We have recorded this. Also, PowerPoints will be later online. So I would just like to remind all students that the deadline for submission is 28 February. So at the end of February 2025. And so then you need to finish and then start jury to look at your design and yeah, to look who actually fulfilled the challenge the best. And as Art mentioned during the first webinar, the best teams will be invited to CLIMA Congress in Milan. ERIHWA is going to pay for maximum of 2 members. You have to come there yourself, but then accommodation and entrance to the conference where you will actually compete with that design will be actually paid for you. So that's, I think that's now from our side. Marie, is there something we have to repeat, remind?
No, I think you went over everything. So that's it. That's it for the webinars. Next step, as you said, is to actually deliver your project by the end of February, and then yeah.
Yeah, and if there are any further questions, then they can write to you via the that email address, and then, as you mentioned previously, then if you don't know the answer, then you will ask any of jury members, so from Italy, from the school, and get the answer. Yes?
Yes, exactly.
Okay. Well, so once more, thank you, everybody, and yeah, see the best ones in Milan.